So to start off, I'd like to declare that I'm both a researcher at the University of Zurich, as well as CEO of Clemedy AG. And Clemedy is a spin-off from the University of Zurich. We are a startup company working in the field of infectious diseases and developing targeted sequencing-based solutions for infectious diseases. And our goal is to develop and commercialize reagent kits and software that will be certified as medical products. Our first application is tuberculosis, and I'd like to give you a bit of an idea of the diagnostic pathway of a tuberculosis patient. So usually you would start with a quick cartridge-based test that can rapidly confirm or reject the suspicion of tuberculosis. The most prominent here is GeneXpert, which in a couple of hours can confirm tuberculosis and as well give resistance information for a single antibiotic used in a standard treatment. You would then move forward with a second molecular test, which will test the remaining antibiotics used in the standard susceptible tuberculosis treatment. That takes another 2 to 3 days, and at the same time you would already start setting up a culture to have phenotypic results. And in the case that you're confronted with a drug-resistant patients, you would actually have to continue testing for second and third line treatment options. And that testing can then take up to 10 weeks. Our goal is to map all of this on the level of the genome of tuberculosis and to be able to test for first and second line antibiotics within 24 to 48 hours. How are we doing this? So we're combining targeted sequencing and machine learning algorithms. And so we have one part happening in the lab where we have developed an amplification panel that is looking at about 120 full-length genes that are known to be involved in drug resistance in tuberculosis. And we will sequence this information, and the sequencing data will then go into the algorithms that can translate that into a diagnostic report. And the two information that the clinician is interested in is knowing the type of tuberculosis that it is, what specific lineage does it belong to, and the second one is the antibiotic resistance information, and from that deriving a treatment options. And that's going to be the focus of this talk, and I'm going to start with showing you the final results. So we have learned machine learning classifiers for 9 antibiotics containing all of the first line antibiotics and a couple of the second line ones. And we have reached here, and they're sorted by accuracy. We have reached sensitivity and specificity between 85 and 99%. And as you can see on the top is the supporting evidence that went into each of the models, and I'll go into details of how they were trained in the next slide. And you can also see that the accuracy achieved is not always reflected in the amount of training data that you have. That will probably show a bit of the different complexity in the resistance mechanisms behind those antibiotics. So how was this plot generated? We've screened about 14,000 publicly available whole genome sequencing data sets that have phenotypic information available. And we have some quality controls, some filtering based on sequencing depths, and then they would be aligned and pre-processed. And then we would call variants for all of these data sets. And here, of note is that we decided to only call variants on the regions that will in the future then be covered by our amplification panel. The variance then gets translated into so-called features for machine learning. We've decided to keep only non-synonymous polymorphisms on coding regions, insertion deletions, frame shifts, premature stop codons, and any other variants as long as it's on a non-coding region. So in total, we have support ranging from around 200 cases to several thousand cases for different antibiotics. And what you can clearly see here is that the first-line antibiotics have much more data available than the second and more exotic treatments that are happening down the line. And that also creates some kind of bias in which most of the cases that are screened for second-line drugs will be resistant to first-line drugs, because else there just wouldn't be an incentive to screen them for the others. We have then a priori selected 4 classes of machine learning models and several parameter combinations, and we're then training about 11 models per antibiotic. And we're validating them using 3-fold cross-validation, where you would train a model on 2/3 of the data and then measure its performance on the remaining third, and you would repeat that 3 times. And the results shown in the previous plot are then the average value of those 3 runs. And then in the final step, we'll choose the best model according to the model with the highest diagnostic odds ratio. So in summary, we have available classifiers to predict antibiotic resistance for first and second line anti-tuberculosis drugs. And we believe that the accuracy is such that, especially coming at such an early point, they could really inform the therapeutic decision made by the clinicians. Our plan is to extend this to novel antibiotics that's been recently included in the second-line treatment, namely delamanid and bedaquiline, for which we'll have to generate our own sequencing data because there's not much publicly available. At the same time, we're working on getting a complete end-to-end workflow going that works directly from a patient sample, and we hope to have that one results for this in mid of this year. If you have whole genome sequencing data of tuberculosis and you want to try out the software, it's currently available on a private genomic cloud, and I have some activation codes with me. So if you want to give it a go, please reach out to me. I'd like to thank the academic partners that we're working with. I'm very grateful also for the support here in Switzerland that is given to startups, the companies that are within our value chain that we rely on, my team, as well as funding from the Von Tobel Foundation and the UZSA Foundation. Thank you very much.